Okay, this is Perfection is Unattainable. This is a video lecture over the ideal gas law and gas stoichiometry. The quote that we have is perfection is not attainable, but if we chase perfection, we can catch excellence. That's Vince Lombardi. Let's look at our learning goals for this lecture. It says that students will understand the kinetic molecular theory, including the necessary assumptions. That's for an ideal gas. Students will be able to use the ideal gas law to solve for an unknown variable. So we'll be able to solve for either pressure, volume, temperature, or moles from that equation. And then students will understand the stoichiometric relationship of gas and how they apply to the ideal gas law. So what we should already know, that pressure, volume, and temperature can vary for a fixed amount of gas. So we looked at the combined gas law and saw that as we change pressure, as we change volume, as we change temperature, that affects the gas. They all affect each other. The key word here is that's for a fixed amount of gas. And so we didn't look at the fact of, well, what if we add more molecules to it? What happens if we change the number of moles that we have in there? What if there's a chemical reaction taking place? And so what we're going to look at now is we're going to start looking and starting adding some of those in. The other thing that we should know is that stoichiometry is a relationship of the matter in a chemical reaction. So how everything's going to react, what happens in those chemical reactions, what's produced, precipitated out. We looked at those things in our stoichiometry unit. And then the coefficients represent the mole ratio in a balanced equation. So in a chemically balanced equation, we see that we have that mole ratio, and that mole ratio will lead to how, back to that stoichiometry on that relationship of how matter interacts in a chemical reaction. Now, in the lab, what we should have learned, and what we were hopefully trying to look at, was that butane has a molar volume of 22.4 liters at STP, so at standard temperature and pressure. This ratio is different if pressure or temperature change. So 22.4 liters per mole is always going to be our relationship that we have if it's at STP. If we change one of the variables, then that number will change. What we see is that 22.4 liters is standard molar volume for all gases. So 1 mole of any gas at STP will have a volume of 22.4 liters. We call that standard molar volume. And so this is hopefully what we got to look at in the lab. So let's look more specifically about what is an ideal gas. Ideal gases, they are defined by the kinetic molecular theory, and we've talked about that. That's the theory that all atoms are moving in any state of matter, that they're constantly moving, and that their movement is related to their temperature. The kinetic molecular theory is a model. It's not necessarily reality. So it's not necessary what's actually happening, but it gives us a model that we can base everything off of. The ideal gases, they work best and operate best at very high temperatures and very low pressures. And really, the best ideal gases are going to be your diatomics, your Brinkelhoff, your hydrogen, your nitrogen, your oxygen, your chlorine, fluorine, bromine, iodine, all of those guys. They're going to be our best ideal gases that we have. Now, there are assumptions that we have to make to have the ideal gases, and these are the 5 assumptions that we have to make. Number 1, that gases consist of tiny particles with extremely low densities. So gases are very small, and they're basically made up just of empty space because there's so many of them in such a large volume. Number 2 is that all collisions are elastic. What this means is you can kind of think of an elastic collision like if you were playing pool, like on a pool table, and the cue ball hits another ball and it just bounces off. An elastic collision, all energy is going to be conserved, and so basically we don't lose any energy in those collisions. Number 3 is that particles are in continuous rapid random motion. And so they really don't have a direction that they're following. They're just kind of bouncing all over the place and they're going really fast. Going back to that kinetic molecular theory that everything's moving. So not only are they moving, but they're moving randomly and they're moving really quickly. Number 4 is that no intermolecular forces. So as the gases bump into each other, they're not going to stay stuck to each other. They're going to be elastic, those collisions and bounce off, and there's not going to be anything that slows them down. So there's nothing in between the molecules. They won't be attracted to each other and slow down. And then number 5 is that the average kinetic energy depends on the temperature. So basically we're correlating the average kinetic energy and temperature. They're going to be related. And basically that only temperature and only movement will have anything to do with the gas. Okay, so let's look at what all gases have in common. Now, the combined gas law held the number of molecules constant. And we're going to look and we're going to change is we're not going to hold all the number of molecules constant. We're going to change that. Now, for ideal gases, all gases that we're going to look at with the ideal gas law and everything else is that 1 mole of gas at STP will occupy 22.4 liters. That's what all gases have in common. That if we're at STP and it's 1 mole, then it's going to be 22.4 liters. And from this idea of that ideal gas at that standard molar volume, what we can do is we can link all the gas laws and create the ideal gas law. So we can start looking at those particles and how they interact. So let's look at the ideal gas law. Basically, it's our PV equals nRT. We call it PIV NERT, where we have our pressure, volume, and temperature, and those units we should be used to. The new guys here that we see are N and R. N represents the number of moles. It's 6.02 times 10 to the 23rd particles. We looked at that way back in the beginning of the year, and we see that R is going to be our ideal gas law constant. And we have two basically definitions or units for it that are two numbers. We can either have our 0.0821 or 8.31. Now basically all of this depends on what our pressure is. If our pressure is in atmospheres, then we'll use this number. If our pressure is in kPa, we will use this number. So it varies, but it just varies depending on what our pressure is going to be. So this is our ideal gas law. Let's go ahead and jump into a problem and let's use it. It says that a 5 gram sample of oxygen has a pressure of 198 kPa and a volume of 148 milliliters. What is the temperature of the gas? Now, when we're looking at this, we have to have the following units. We have to have liters, we have to have moles, and we have to have Kelvin. And our pressure can vary depending on our ideal gas law constant. Since this is kPa, we will use the ideal gas law that has kPa in it, so 8.31. So what we'll do is we'll leave the pressure the same, and we'll write that down in our given. Remember, use the guess method. So our given is our pressure will equal 198 kPa. Okay. The other thing that we're going to have is we always have our ideal gas law constant. We just have to pick which one we're going to use. And since we have our kPa, then we use our ideal gas law constant. So our R value of our 8.31 would be our ideal gas law constant. Now, the other things that we have a volume, but remember our volume has to be in liters, because if you look at the units for our ideal gas law constant, it is liters, kPa, moles, and Kelvin. So we have to have those units to be able to use that R value. So what we have to look at is our volume is going to be 148 milliliters, which we need that in liters. So to convert from milliliters to liters, we divide by 1,000 and we'll get 0.148 liters. And then lastly, we just need the other thing we're given is grams. Now, anytime it gives us grams, we can convert from grams to moles using molar mass. So our N value that we're going to get is going to be our moles. Well, to do that, we see that it is oxygen gas. So we have 5 grams of O2, and all we need is our molar mass. So we know that 1 mole of O2 gas is 32.00 grams of O2 gas. And we just got that off the periodic table. 1 atom of oxygen is 16, and we have O2, so it's 32. So we put our 32.00 grams, 1 mole of O2 on top. We go ahead and work that out, and we will get an N value of 0.156, and that would be moles. So there's our given. It says, what is the temperature? So we're looking for temperature. That's our unknown. And then we just go ahead, and our equation is PV equals nRT. We're solving for T, so we divide by N and R. So we get PV equals all over nR equals T. We go ahead and plug all of this in, and what we'll get is we will get our T equaling our 198 kPa times our 0.148 liters, all divided by our 0.56, or sorry, not 0.56, but 0.156 moles, and then our 8.31, which is our ideal gas law constant. And we will get a temperature, and this temperature will be in Kelvin, of 22.60 Kelvin. It's a very cold temperature. Let's move on to our next one. Example A2. It says a sample of nitrogen gas has a pressure of 8.7 atmospheres, a temperature of 48 C, a volume of 28 mils. How many molecules of N2 are present? So we're looking for molecules. Now if we look at our equation, PV equals nRT, if you look at what we're given, we have a pressure equaling 8.7 atmospheres. We have a temperature, which once we convert it to Kelvin, because we always convert it to Kelvin, is 321 K, and we have a volume of 2.8 liters. Now remember, we always have our R, and in this case it's going to be in atmospheres, so we're going to use the 0.0821 for our R value. And then if you look at our equation, what we're given pressure, volume, temperature, we have R. So the only unknown that we have is N. Now remember what N solves for. N is going to give us moles. Okay, it's asking for molecules. So we'll have an extra step at the end that we'll have to do, but we're going to first solve for moles. So we take this and we go ahead and we plug it in, and we will get our 8.7, and first we have to use our equation, forgot the E, equation, PV equals nRT. Solve for N, we'll get PV all over RT equaling N. So plug everything into this, and we get our 8.7 atmospheres. And then that times our 2.8 liters all over our 0.0821. There's our R value in 321 Kelvin. Once we plug this in, we'll get an N value of right around 0.924 moles of our nitrogen gas. So now we have moles. So all we have to do is convert it from moles into molecules. Well, to do that, we need to remember that 1 mole of N2 equals 6.02 times 10 to the 23rd molecules of N2. So all we have to do is do a little bit of dimensional analysis and take our 0.924. So 0.924 moles, set it up, and 1 mole equals 6.02 times 10 to the 23rd molecules. And once we plug that into our calculator, work it out, we will get an answer of 5.56 times 10 to the 23rd, and that would be molecules of N2. Alright, so let's start looking at the ideal gas law and stoichiometry. Now, we can relate the ideal gas law to chemical reactions through the value of N, through that value of the mole. When gas is produced in a chemical reaction, we can use it to calculate pressure, temperature, and volume. And so through that value of N, we can relate it back to all of the stoichiometry that we did in chemical reactions. So let's look at an example of how we do this. So example B1, it says when zinc is placed in hydrochloric acid, so we're putting zinc in hydrochloric acid, a single replacement reaction occurs and produces hydrogen gas and our zinc chloride. A 5-gram sample of zinc is placed in a beaker with excess hydrochloric acid, so we know that zinc is going to be our limiting reactant, and allowed to completely react. The hydrogen gas is collected, and the pressure has a pressure of 825 millimeters of mercury and a temperature of 55 degrees Celsius. This is what is the volume of the hydrogen gas. So if we look at what we have 5-gram sample of zinc. That's not what we're looking for. We're looking for volume of hydrogen. So we look at this. Let's look at what we're given of hydrogen. We're given a pressure of 825 millimeters of mercury, and we're given a temperature, which let's go ahead and convert that into Kelvin. We get 328 Kelvin. And that's all we're given. Now we know that we have our R value when we're looking at this, which we know that our R value is going to be either in atmospheres or in kPa, so we'll keep it in atmospheres. And that means that we have to convert this millimeters of mercury, but we'll say our 0.0821 is our R value. So the two things we're missing N and we're missing V. Now, we're solving for what is the volume, our unknown. So here's our given. Our unknown is going to be the volume of hydrogen gas. That's what we're searching for. So to find that, we have to have N, which N is the number of moles of our hydrogen gas. Well, we can calculate that because it tells us that we have 5 grams of zinc. So we're going to use stoichiometry to figure out how much hydrogen is produced in moles, and then we'll plug that into our N value, and then we can solve for V. So the first thing that we need when we're working this out is we need a nice balanced chemical equation. So zinc is Zn, hydrochloric acid, hydro is a binary acid, and so it's hydrogen bonded to chlorine, which is when we crisscross those we get HCl. Now it tells us it produces our hydrogen gas, which hydrogen is a diatomic, it's H2, plus zinc chloride, which zinc always has an oxidation number of 2, so we have Zn plus 2, chlorine minus 1, we crisscross, and we get our ZnCl2. This is our equation. Now we have to balance it. We have 1 zinc on the reactants, so 1 zinc and 1 zinc. So we're good there. Okay, look at our hydrogens. 1 hydrogen and 2 hydrogens. Not good there. So let's go ahead and we'll put a 2 right here, and we'll balance it out. And we see that now we have 2 chlorines and 2 chlorines. Everything's balanced. So we're starting with 5 grams of zinc. That's what we're starting with. So we're dealing with zinc, and we want to figure out, it says, what is the volume of hydrogen gas. So we're dealing with our zinc and our hydrogen. And we're starting at grams here. Now we just want to go to moles of hydrogen, so we don't need the molar mass there. So the first thing we write down is our mole ratio, which our mole ratio is just 1 to 1. So 1 mole of zinc equals 1 mole of H2. And since it said grams, we're starting with grams of zinc, we need the molar mass of that. So 1 mole of zinc equals the molar mass of zinc, which is 65.38 grams of zinc. Okay, so we set up our conversion, and now all we do is plug in our conversion factors. So we need grams of zinc on the bottom to match that unit. So that goes on the bottom. The other part goes on the top. Okay, now we're not 2 moles of hydrogen yet, so we keep going, and we put, since this up here says moles of zinc, we put moles of zinc on the bottom, which that would be our 1 mole, and then we put the other half on top, which is right there. And then we go ahead and we multiply everything out, and we will get the number of moles of our hydrogen gas is going to be right around 0.0765, and that would be moles of H2. So that's going to be our N value, so our 0.0765 moles of H2. And then what we do is we take that, this is our given, we find our unknown, let's write our equation, PV equals nRT. We're going to solve for, it says what is the volume, so we're solving for V, it's our unknown. So we will get our volume equals our, and all we do is divide by P, and our volume equals our value of our 0.0765, that's our moles. Our value is 0.0821. Our temperature is going to be our 328 K, and then all divided by a pressure of, once we convert this, and don't forget we have to convert that into atmospheres, and to do that we just divide by 760, and we get that as 1.086. Once we convert that to atmospheres, dividing by 760, we get a volume of, so our volume of our hydrogen gas is going to be right around 1.897 liters. All right, let's look at this one. It says example B2, water decomposes to produce hydrogen gas and oxygen gas in the following reaction. Gave us the equation. It says if a sample of oxygen is collected that has a pressure of 1.9 atmospheres, 34 milliliters, and a temperature of 64 degrees Celsius, it wants to know what is the mass of the water used in the reaction. So we're searching for the mass of water. Let's look at what we're given. We're given a pressure which equals 1.9 atmospheres, a volume, which we know it can't be in milliliters, so let's just convert that to liters by dividing by 1,000, of 0.034 liters, and then a temperature of, we can't keep that in Celsius, so let's go ahead and convert that to Kelvin by adding 273, which is 337 Kelvin. So we have a pressure, a volume, a temperature. Remember, we always have R. Since this is atmospheres, we'll use 0.0821 for our R value. And so it's looking for mass of water. And it says that the oxygen was collected. So we collected this, and we're trying to figure out the mass of water that we started with. So when we're working this out, what you can figure out is that the value that we don't have in PivNert is N. Well, N will give us the moles of water, and then what we can do is use the moles of water to convert into, or sorry, moles of oxygen, and use that to convert into moles of water. So we find N, and that'll be of oxygen, and we use that to convert to moles of water. So let's go ahead and start with our PivNert. So we have our PV equals nRT. We have this right here, so we're solving for N, so we'll get PV equals, all divided by RT equals N. And so we plug everything into the equation, and what we will get is we get N, which equals our 1.9 times our 0.034 liters all over our 0.0821. And that's our R, and our T of 337 K. So we go ahead, plug that into a calculator, and we will get an N value, or moles of oxygen, of 0.00233, and that would be moles of O2. Okay, so if we're looking at our equation, if we have moles of O2, how do we go from moles of O2 to grams of H2O? So we want grams of H2O. The first thing we write down is our mole ratio, which when we look at this, our mole ratio is 1 mole of O2 equals 2 moles of water. So we write that down. 1 mole of O2 equals 2 moles of water. Now, since we're going to grams of water, we need the molar mass of water. So 1 mole of water equals our 18.02 grams of water. Okay, so there's our conversion factors that we're going to use. Let's start with our moles that we have of O2. So 0.00233 moles of O2. Set it up. We have moles of O2, so on the bottom we put moles of O2. Put the other half of the conversion on top, 2 moles of water. Okay, now we don't have grams of water yet, so we keep going, and we match up our units, moles of moles, and then we put the grams on top. And we go ahead and multiply the top, and it'll give us the grams of water, which is 0.084 grams of our H2O.